Hello, bonjour, Kamai, Aingai. Welcome to the 6th week of Statistical Mechanics, Algorithms and Computations from the Physics Department of École normale supérieure. We are right now in the middle of our 3-week module on quantum physics and quantum statistical mechanics. And we have just started our second half of this lecture course. So let me start with a brief exposition of where we have come from and where we stand right now. This exposition will be in the light of what we already learned about the connection between sampling and integration. So, 5 weeks ago, we started by considering pebbles on the Monte Carlo beach and on the heliport. The partition function was the integral in x from -1 to 1 and the integral in y from -1 to 1 of pi of x and y, which was a constant equal to 1. We then moved to a discussion of hard disks. The partition function now was this integral with the statistical weight pi of x, which was equal to 1 if the configuration was legal and 0 if it was illegal. Last week, we then moved to a discussion of quantum physics. The partition function now was the path integral over dx0, dx1, and so on, dxn-1 of the statistical weight, which was the density matrix between x0, x1, beta over n, density matrix of x1, x2, beta over n, density matrix of xn-1, x0, beta over n. This is the path integral. We sampled it using a naive path integral Monte Carlo algorithm that resembled what we already did for hard disks. But rather than picking one disk at random, we picked one bead at random. Then we moved it a little bit to the left or to the right and accepted it with the metropolis acceptance probability. This week, we will remain within this picture of quantum physics. We will present a providential sampling algorithm that goes back to Paul Lévy in 1940. It is a rejection-free, direct sampling algorithm, something we never achieved for hard disks. Let me briefly explain what the Lévy algorithm achieves. You pick a starting position x at tau equals to 0 and a final position x prime at tau equals to beta. And then, check, you fill in the path between x and x prime in one setting. You can do this with a number of slices that is as large as you want, 100, 1,000, or 1,000,000. Here we have a free particle, but an analogous Lévy construction exists also for a particle in a harmonic trap. Lévy's algorithm is really famous, and not just in quantum statistical mechanics. It exists under various names in the physics of interfaces, in numerical analysis, in statistics, in financial mathematics, and in electrical engineering. The path you see here illustrates the Heisenberg uncertainty principle, the founding principle of quantum mechanics, and one of the pillars of quantum statistical physics. At low temperature, large beta, the path fluctuates wildly, and this means that the particle position x is uncertain. Next week, the Lévy construction algorithm will be a crucial element of many-body simulations. And then we will fathom the second pillar of quantum statistical mechanics, the indiscernibility of particles and their bosonic or fermionic nature, and the curious Bose-Einstein condensation. To discuss Bose-Einstein condensation, we will again mostly use the path integral language. But to understand why this is a condensation, we need to consider wave functions and energy levels. And this is what we will do in this week's tutorial, where we will get down to the heart of bosonic statistics and will solve a model of a finite number of particles, a small number of particles, in a three-dimensional harmonic trap. In this week's homework session, we consolidate what we learned in the lecture through practical calculations. For simplicity, we remain within the framework of the harmonic potential. But the firework of sampling strategies and re-weighting schemes applies to a much wider range of problems than just to a poor little quantum particle in a harmonic trap. Again, you must understand the great range of applications of our concepts inside and outside of physics. Quantum paths are closely related to interfaces, as you see here for an interface between two liquids. Quantum paths are also closely related to what is studied by financial analysts. So, let's get started with week 6 of statistical mechanics, algorithms and computations. We recall once more the final subject of last week's lecture. We arrived at the representation of the partition function of a quantum particle in a harmonic potential as a sum, or rather as a multiple integral over paths with a statistical weight giving the weight of each path. You see, the partition function really is a sum over all paths. We sampled this partition function using a naive algorithm, naive harmonic path.pi. Its key element was that we sampled a random bead k and proposed a random move from xk to xk plus delta x and accepted or rejected the move with the metropolis acceptance probability. Naive harmonic path satisfies detailed balance, is aperiodic and irreducible, but it is painfully slow. If we start at a configuration as the one shown here, the next configuration will be very little different from the one that we have already, because we only move one bead and we move it only by a little bit. If we made larger moves, we would get into trouble with the 1/2 rule. We would reject all the moves and would not move either. So you see that a simulation using naive harmonic paths would be very, very slow in exploring all configurations in our system. To make progress, let us move back by 2 steps. First step, we take away the harmonic potential and consider a free particle. Second step, instead of sampling a value of k at each step, we keep k fixed. We move particle xk for fixed values of xk minus 1 and xk plus 1 as programmed in naive path slice.py. So we move xk with the Metropolis algorithm. And here is the histogram of the positions of xk. It looks like a Gaussian. And in fact, it is a Gaussian, because the probability pi of xk is put together from the density matrix rho free between xk minus 1 and xk, and rho free between xk and xk plus 1. The two are Gaussians, and their product is also a Gaussian for xk. So the distribution pi of xk is a Gaussian with mean value xk minus 1 plus xk plus 1 over 2, and the variance sigma square equals to delta tau over 2. Now, there is no reason in the world to use the Metropolis algorithm, as we know that the distribution of xk is a Gaussian. We should sample xk from this Gaussian distribution with the correct mean value and variance. You might be interested to implement this idea in your version of naive harmonic path, as we did here for the free particle. But rather than doing it, let us slightly generalize this problem and consider a position xk sandwiched between position x prime and x double prime with intervals in tau, delta tau prime and delta tau double prime. The probability distribution of xk given x prime and x double prime is the product of two free density matrices. The density matrix rho free of x prime, xk, delta tau prime, and the density matrix rho free of xk, x double prime, delta tau double prime. Both these density matrices are Gaussians, and their product is also a Gaussian. Putting all this together and noticing that in this distribution xk is the variable and x prime and x double prime are fixed, we find that the probability distribution pi of xk given x prime and x double prime is a Gaussian with mean value and variance as shown here. Before continuing, please take a moment to download, run and modify the programs we discussed in this section. On the Coursera website, you'll find the program naive path slice.py that treats the case of one variable xk sandwiched in between x prime and x double prime. This is an innocent little program, but it should convince you that the above formulas that we used are correct. In any case, running this program, you will understand that using the Metropolis algorithm in this situation is useless. You might just as well sample xk from the appropriate Gaussian. Then again, you'll find the naive harmonic path.py. in this algorithm, you could replace the metropolis algorithm for the xk by the Gaussian direct sampling. But better wait for greater things to come. In naive past sampling, we propose xk with a flat distribution and accept it with a Gaussian. The mismatch between proposed and accepted moves generates, of course, the rejection rate in the metropolis algorithm. We could modify the naive past sampling algorithm by proposing xk with the appropriate Gaussian distribution, and there would be no rejections anymore. But we can put the conditional probability pi of xk to much better use. In fact, pi of xk given x prime x double prime gives the statistical weight of all paths that start at x prime, that pass through xk, and that end up at x double prime. Let's apply this idea for xk equal to x1, x prime equals to x0, and x double prime equal to xn. We can sample the position x1 given x0 and xn. Between the freshly sampled value of x1 and xn, we can then sample the value of x2, and then of x3, and then of x4, and eventually the entire path. In Python, this gives the following little algorithm, Lévy freepath.py. And look here at the configuration of a path with n equals to 50,000 produced by Lévy freepath.py. It has no correlation with previous paths, and its construction has caused no rejection. In the limit n going to infinity, x of tau is a continuous function of tau. As a curiosity, let us discuss for a moment the return condition that makes the Lévy construction non-trivial. The path has to return to the position x prime at tau equals to beta. Without this return condition, we would simply have a random walk, and we would sample the position x1 from the given position x0. Then we would sample the position x2 from the given position x1 as a Gaussian. Then we would sample x3 from x2, x4 from x3, and so on until xn from xn minus 1. The partition function of this problem would be written as z of the random walk is equal to the integral over x1, x2 until xn of the density matrices row free of x0, x1, beta over n, until xn minus 1, xn, beta over n. And notice that we would sample over the position xn, that means we integrate over the variable xn. This is implemented in the algorithm continuous random walk.py. But of course, the probability to hit the position x prime at tau equals to beta, the probability that xn is equal to x prime is equal to 0. Now, let me tell you of a simple algorithm the trivial path.pi that will rectify the situation. What you can do, you sample the Gaussian random walk that goes to xn rather than to x prime. Then you pull back the position xn by the value of xn minus x prime. And then you pull back all the intermediate positions by a value proportional to xn minus x prime multiplied by tau over beta. This algorithm produces output which is indistinguishable from the output of the Lévy construction, but I leave it to you as an exercise to prove this. Before moving on to the next section, please take a moment to download, run and modify the algorithms we discussed right now. There is the algorithm Lévy free path.pi. In this algorithm, you really can modify many aspects. There is no reason to first sample x1, then x2, x3, and so on. You can rewrite your algorithm so that it first samples xn over 2 and fills in the paths in the lower and in the upper half separately. Then there is the algorithm continuous random walk.pi and the mysterious pullback algorithm trivial free path.pi. Try to understand, at least empirically, that this algorithm gives exactly the same output as the Lévy construction. We have sampled so far 3 quantum paths, continuous non-differentiable objects that correspond to the free Hamiltonian. This is possible because the free density matrix is a Gaussian, and product and integrals of Gaussians are again Gaussians. For the harmonic density matrix in Trotter approximation, the same is true. It is given by a product over 3 Gaussians, 2 for the Trotter formula and the potential, and 1 for the free density matrix. So at high temperature, small beta, the harmonic density matrix is given by an exponential of 2 terms, one in x minus x prime square and one in x plus x prime square. Under matrix squaring, the harmonic density matrix keeps this form. And an exact calculation shows that the explicit formula for the harmonic density matrix at all temperatures is given by this expression. The diagonal term, rho harmonic of x beta, is given by an exponential of minus x squared times the hyperbolic tangent of beta over 2. The fact that it is a Gaussian allows us to derive an algorithm for the Lévy construction of a particle in a harmonic trap. This is Lévy harmonic path.pi, and it is as simple as the free Lévy construction. Again, we can now choose a configuration x at tau equals to 0 and x prime at tau equals to beta. And the algorithm fills in a configuration, a path between 0 and beta, without rejections and without using Markov chain methods. Of course, the path is now constrained through the harmonic potential, and its extension is fixed by the oscillator strength omega and the temperature. Before continuing, please take a moment to download, run and modify the program we just discussed, Lévy harmonic path.pi. Besides this program and the graphics version, you will also find a short fact sheet that gives the relevant formulas and derives the harmonic density matrix through matrix squaring. You also find on the website a multidimensional version of this program. You have no problem understanding that a three-dimensional quantum path can be sampled by independent Lévy constructions in X, Y, and Z. In this lecture, we have studied the path integral picture of quantum statistical mechanics and the providential path sampling algorithm that goes back to Lévy in 1940. In free space and in any dimension, this algorithm allows to sample a path from a position x at time tau to x prime at tau equals to beta. Notice that in this picture we are discussing a quantum system in one dimension, x. But it looks like a classical line-shaped object in two dimensions. It is for this reason that one says that a quantum system in one dimension corresponds to a classical system in two dimensions. Or more generally, that a quantum system in dimension d corresponds to a classical system in d+1. As the temperature gets lower, beta gets higher, and the extension of this space in all dimensions becomes infinite. As we discussed, the Lévy construction also exists for particle in harmonic potential. And we will rely heavily on this, well, you will rely heavily on this to create your own Bose-Einstein condensates that resemble very much the experimental condensates that were created in this glass cell. So now it is time for you to download and run the programs that we discussed and to create quantum paths like the one shown here. Create your own quantum path with hundreds and thousands of points. Then print it out on glossy paper, make yourself a frame and hang it up in your room. As mentioned, there are many exciting subjects that we will discuss in this week's tutorial and that you will discover in this week's homework. So thanks for your attention and see you again next week in statistical mechanics, algorithms and computations for a week devoted to Bose-Einstein condensation.